So basically, we're going to work on hyperparameter tuning in order to improve the accuracy. Not only the accuracy, we are also going to work with few other parameters like true positive, false positive, right? And in some cases, we are also going to be worried about true negative and true false negatives, right? In order to improve these things, let's say, for example, true positivity has to be improved and false positive has to be reduced in some cases, right? So to avoid those and to decrease few and to improve few scores, we are going to work on something which is called as hyperparameter tuning. Now, I hope you're able to see my screen. No, you're not. Right. So we are going to work on something which is called as hyperparameter tuning. Right? To improve your accuracy, TP, reduce your FP, ILA, we have few cases where we need to improve our model. So that's where your hyperparameter tuning comes into the picture, right? Now, post this hyperparameter tuning, there are some effects which are going to erase, right? There will be some effect on your model when you're going to improve the hyperparameter tuning, or you're going to experiment with your hyperparameters, right? And that is called as your overfitting and underfitting. Overfit and underfit. Now, what do you mean by this overfit and underfit? Right? Basically, when I say overfitting, right? When I say overfitting, where the train data accuracy is more than your test data, right? నందిత గారు మీకు నా వాయిస్ క్లియర్గానే ఉంది కదా, వినిపిస్తుంది కదా?
యా వినిపిస్తుందండి.
ఓకే, ఫైన్. సో వేర్ ది ట్రైన్ డేటా is good, has good accuracy than your test data. Now, ఈ టాపిక్ గురించి మాట్లాడుకునేటప్పుడు I just want to rephrase few things. That is your data splits. Just give me 1 second. I'm sorry about it. My bad. Now, when we are actually talking about this overfit and underfit, we are actually going to discuss, I mean, we were actually discussing about the train accuracy and test accuracy. Now, when this test accuracy and train accuracy comes into the picture, I just want to quickly have a refresh about the split of data. Now, whenever we have the raw data, right, we're going to clean the data. Just for your reference, when I say clean the data, you're going to work with outliers, missing values, right? And also, we're going to work on something which is called as feature engineering. Right? And then your conversion of data into a vector format. For that, we are actually going to use a few techniques. I hope you remember it. Now, post that, right, we're going to split the data. Now, what do we use to split the data? Obviously, we use a package which is called as test time split from sklearn, and we are going to work with that. But here, whenever we are going to split the data, generally what we do is, let's say if we have 100 records of data, which means 100 rows of data, we split this into 80, 20, or 70, 30, right? And this split will be a random split, right? Randomly, we are going to pick few cases and then we are going to update here, update into a test or train data. But for the models which we are going to work in future, like your ensemble techniques and also your deep learning techniques, we are not going to split the data into test and train, not into two parts. We're going to do it into three parts. Now, what will be the third part called as? It will be called as validation set, right? And this validation set will be a subset of the 80% of the train data which you have taken. Now, let's say an example here that if I'm going to split this 100 records into 80% of trained and 20% of test, I'm going to take a subset of this 80 records and split it again for 60 into train and another 20 into validation dataset, right? In order to understand the model even better. Now, even before discussing about your overfit and underfit of the data, we have a couple of topics or we have a couple of terms, which we have to discuss. And they are called as bias and variance. Now, what do you mean by bias? My explanation will be basically in layman terms. That means anyone who listens it within a one shot, it will be easy to understand. So that is the way I'll explain it to you. Bias is nothing but when a model is too simple and it cannot capture the patterns which are present in the data. That's where the bias is going to happen, which means your trained data validation or trained data accuracy is going to be low and your test data accuracy is going to be high, right? That's a scenario of underfit. But when I say bias, let me repeat the term again. When I say bias, when the model is too simple, without any hyperparameter tuning, where your accuracy is very low, and if you give a complex part of or a complex pattern to identify with your model which you have built to predict, there if the model predicts to classify it, right? In that case, we call it as a bias model, right? We call it as a bias model, which basically bias is nothing but a too simple model. Too simple model. Now, what happens with this too simple model, basically, that the entire data when you try to predict, even now, if you have built the machine learning model with your trained data itself and you try to predict this trained data, it wouldn't be 100% or it wouldn't be 90%. It would be somewhere around 60% or 50%, right? So that's where your bias is going to occur. And this bias is directly linked to your underfitting, and also called as underfitting of your data or model, right? An example which I would like to take here is, let's say if you have a use case which is for predicting house prices, right? Just by just on the basis of size of house. It's a simple regression model, simple linear regression model, and where you are taking the size of house and you are trying to predict the price of house, right? There are no other parameters like location, number of rooms, number of bedrooms, number of bathrooms, right? Garage, yes or no, right? So these kind of parameters are not present. There, the model is built very weak, right? And the predictions here is going to be very poor, right? Because the model is very simple to the data, right? So that's where we get a lot of wrong predictions, right? That's about your bias. Now, when it comes to variance, it's quite opposite to your bias, where model is very complex, right? Now, that's where your hyperparameter tuning comes. Tuning of your over tuning of your model leads to higher variance, right? Where your train accuracy is more and your test accuracy is very low, right? That's where your variance is going to come into the picture, right? Even the smallest small detail which you have in your data is considered, right? There, if you are actually fitting the entire data to your machine learning model, right, that's where your overfitting happened and variance is going to be high. Now, where you are actually going to see these variance and biases, you're going to see all these in your model summary. I'll show it to you once when I start to build a machine learning model and give it to you. But just understand the terms here so that it would be no new when we are actually building a machine learning model, right? Now, when I say variance, as I told you, it's completely opposite variance, where I say that it's too complex model, right? It's a too complex model. Now, where this overfitting or high variance is going to occur, or where can we actually see a higher variance? Now, basically, whenever we are trying to build a deep learning model, neural network model, where we are trying to classify an image, right? There we can actually see something which is called as higher variance. And also, there is a model which is called as decision tree. Now, you might know about decision tree, which is nothing but where you are going to learn the data and understand about the data, and a tree type structure is going to build where it's going to and highlight each and every data point, and it's going to crawl through it, right? There, you're actually going to see overfitting of data. Now, how does your decision tree model, going to work with under overfitting? There is a technique which is called as pruning, right? Whenever you get a time, just have a look at something which is called as pruning. Now, what does this pruning do? It only takes the important things or uh, important parameters which are present, right, from the data, and it's going to build a model where it's not going to overfit the data to the model, right? Overfit the model, right? There it's going to work. Pruning is going to take care of that, right? So this is about your hyperparameter tuning, and transitioning from that hyperparameter tuning, we are going to work with something which is called as overfitting and also underfitting. Now, as I told you, what do you mean by overfitting? Let us start to talk about overfitting first and then move ahead with underfitting next. Nandita గారు మీకు క్లియర్ కదండి ఇది?
యాహ్! అండి.
ఫైన్.
సారీ
సో
నేను సౌండ్స్ ఒస్తాయి. సో, అందుకనే
పర్లేదు
పెడుతున్నా.
పర్లేదు, దానిదేం
యాహ్!
ప్రాబ్లం లేదు. సో moving next in, what we are going to discuss is called as overfitting. Now, why overfitting has been highlighted in your syllabus? My bad. Overfitting Now, this is a very, very important thing for your machine learning model. Now, on a brighter side, underfitting is very good because now the reason why I say that is because you can actually handle underfitting by improving the hyperparameters. But when it comes to overfitting, it's very hard to handle it. Right? Now, the reason why I say this is because a simple example which I would like to take here is, let's take a student whose name is Sahit. And Sahit's teacher is Samuel. And Samuel has taught Sahit everything about data sciences and everything, and he has started to work with him. Right? And someone from some third person came and questioned Sahit about data sciences. Right? And he was not able to answer. That's fine. Right? The reason that's fine is because he will be able to learn about the data sciences now or next, and he might start to work on it. What if Sahit tried to understand everything what has been taught by Samuel, and he starts to post an extra information to the third person who comes and asks than what he is asking? That's where the danger comes ahead. Right? When your model is too complex, right? When your model is too complex, there, obviously, your prediction is going to be very good. But on the other side, right? On the other side, just give me 1 second, my bad. Right? My bad. I'm very sorry about it. Yeah. On the other side, he will be only knowing about this data science. Beyond this, if any other question is being asked by the third person, let's say about data analysis or data engineering, there he might not answer anything. Right? That's where the overfitting is going to come into picture, where the train accuracy is more and your test accuracy is low. And please remember one thing, we are not actually talking about true positive, true negative, false positive, false negative. We are not considering those into the picture, right? When I say accuracy, right, it's nothing but a formula which you might all know, that is nothing but true positive plus true negative by true positive plus true negative plus false positive and false negative. I hope you know the formula, but let me write it down here. The reason why I'm actually telling you is just because I'm actually talking more about accuracy rather than a individual classification, right? It's TP plus TN by TP plus TN plus FP plus FN. So I hope you know about these TP, FP, FN, and TNs, right? Or you want any kind of explanation around this? నందిత గారు మీకు ఇది ఓకే కదా? ఐ మీన్ టీపీ, టీఎన్, ఎఫ్పి, ఎఫ్ఎన్స్ అనేవి ఎట్లా క్లాసిఫై చేస్తారనేది?
యాహ్! తెలుసండి.
Right. So the reason why I'm more focused on accuracy is because the overall accuracy decides how good a model is classifying. Right? That is the reason why we are more focused on the accuracy part itself. And when it comes to overfitting and underfitting, we are actually taking care and working with only train and test accuracies. But on the brighter side, we also have to look at other parameters like your true positivity, the number of correct predictions which are done by your model, positive predictions which are predicted as positive, and number of negative predictions which are predicted as negative. And a very, very important thing for your any machine learning model, a parameter which you have to look at is called as FP. Now, If the score of FP is low, that's where you can say that the model is predicting really good. Right? Now, the reason why I say this is because false positive is a very dangerous thing when it comes to an actual model presentation. Right? Now, let us get back to our overfitting. Right? As I told you previously, where the variance is really high, right? Where variance is very high, the model is very complex, and the data which has been, modeled, where it starts to learn the underlying patterns, noise, and everything which is present in the data, right? And it performs really good with your test trained data, but has a low accuracy with your test data. That's called as your overfitting of model, right? This indicates that the model is too complex and memorizes the trained data, right? And memorizes the trained data. That's where the issue arises, right? So high train accuracies and low test accuracies, right? This is where your overfitting does. Now, anyhow, we can fix an underfit model by, improving the hyperparameters, splitting the data once again, or improving the split quality, right? Such a way you have a lot of things to be done that can be done for underfitting data or underfitting model. Now, what can we actually do to prevent a model from overfitting? So I shouldn't be saying this, but preventing cannot be done with an overfitting. You actually will be able to know once you fit the data to a model if it is underfitting or overfitting, right? Once it's been done. Now, there are a few simple steps which we can follow. That is simplifying the model. Simplifying model. Now, what do you mean by simplifying the model? Using few parameters, right? Or a simple model architecture, right? Now, when I say simple model architecture, now let's say, for example, if it is XGBoost without any hyperparameters, sorry, I shouldn't be talking about XGBoost because that's the next topic. Let's take decision tree or linear regression. Without any hyperparameters, we are actually going to fit the data and we are going to check the scores. If the scores are underfit, not so good with the accuracy, then we are going to introduce hyperparameters and then we are going to work with that, right? Now, again, we also have something which is called as regularization techniques. A simple parameter which is called as regularization techniques. So we have L1 regularization and L2 regularization, lasso and ridge regularizations, right? So they help you to prevent overfitting of your data by keeping the model weights small, which means the sample of data where each and every iteration of data is going to pass through your model is going to be reduced, right? That's where your regularization comes into your picture. Regularization comes into picture. Now, moving ahead, the third point which I'm going to tell you is specific for your a specific data type which is called as image. Now, this is called as augmentation. Now, what do you mean by augmentation? Now, when I say augmentation, this augmentation is only applicable for your image data, right? If you remember, we have actually discussed when we were actually working about data augmentation, where we are going to flip, rotate, or alter the image, right, to generate a better model. or better images to model, right? Now, let's say, for example, I have an image of a car, right? I really don't have an image of car right away. So just imagine that you have an image of car, 15 different cars, and that data is very less. Now, if you want to improve the model, if you want to improve the test score, basically, what you are going to do is we can't generate the data, right? In that case, we're going to flip the image. We are going to rotate the image by 150 degrees or 180 degrees. That would be a new pattern for model to identify a class, right? Or we're going to alter an image by adding a layer on it, making it blur or 50% visible, or changing the colors in it, right? So these are called as alteration of images, right? And this data augmentation is specific for your images only, right? And finally, we also have a technique which is called as cross-validation. Now, what do you mean by cross-validation? I hope you have already gone through it, where we are going to experiment with different parameters sequentially, work with one parameter, and then we are going to move ahead with that. And there we are actually going to estimate the errors and basically get an estimation of best fit model with the hyperparameters, right? That's where the steps we are going to follow to avoid overfitting, right? I hope this is clear for you till now. Is it okay? Can I move ahead with the next topic? మెసేజ్ చేయండి పర్లేదు. నందిత గారు ఓకేనండి, నెక్స్ట్ టాపిక్ మూవ్ అవ్వచ్చా? రైట్, ఐ హోప్ ఇట్స్ ఫైన్. సో నేను నెక్స్ట్ టాపిక్ అయితే మూవ్ అవుతున్నాను, బట్ లెట్ మీ నో ఇఫ్ ఎనీథింగ్ కమ్స్ అప్ ఇన్ మిడిల్. సో నెక్స్ట్ టాపిక్ వచ్చేసరికి ఏంటంటే వీఆర్ గోయింగ్ టు డిస్కస్ సంథింగ్ విచ్ ఇస్ కాల్డ్ యాజ్ ensemble technique. Ensemble technique. Now, when I say ensemble technique, what do you actually mean by ensemble technique? Why are we going to work with ensemble techniques? Basically, ensemble technique is nothing but there are two techniques which we are going to work with ensemble techniques. Under ensemble technique, we're going to have two models which are called as bagging and boosting, right? Under ensemble technique, you have two models which are called as bagging and the other type of model which is called as boosting, right? Now, what do you mean by this bagging and boosting? What are the models which do come under this bagging and boosting? Now, let us discuss about bagging first. What is the main, focus of this bagging model, and how does this bagging model to work, right? And what are the key points for the bagging? Now, when I say bagging, what models do come under this are basically your random forest and decision tree models. Random forest, decision tree. These are the two models which come under your bagging. And bagging model, basic bagging technique basically focus on reducing the variance and preventing the overfitting, right? This is the basic understanding or basic agenda for your bagging model. Now, how does your bagging model work? There is a technique which is called as bootstrap technique whenever a machine learning model is going to build. There is a technique which is called as bootstrap sampling technique. Now, what does this bootstrap sampling technique does do is, let's say this previous example which we have took just now, that is, a data is divided into 80-20, 80 and 20. Now, out of this 80%, when a random forest model has been built, random forest is nothing but a combination of multiple decision trees which are run parallelly. I hope you know about it, right? Now, when a random forest model is being built, there are multiple decision tree models which are built parallelly in the backend. Now, what happens with this bootstrap sampling technique is there are multiple subsets of this particular 80% data which are created, right? There are multiple, I'll repeat it once again, there are multiple subsets of this 80% data which are created, which will be the replacement for this 80% data, the samples. And each model will be trained with a different subset of data. Now, for example, this 80% of data might be divided into 100 different data sets or 100 subsets. This is example. This is not an accurate explanation of how the subset is going to work. Bootstrap sampling is going to work. Just for your understanding, I'm doing it in this way. Or let's say, for example, 10 samples, 10 subsets. Now, when you are trying to build a random forest model, each subset is going to be taken as a base learner to train different models, right? And with your bagging, what happens is multiple decision tree models are built parallelly. Now, when I say parallelly, as I told you, this 80% data is divided into 10 subsets, and these 10 subsets, right, are going to be fit to 10 different decision tree models, and they are built parallelly at a time, right? And we focus only on one thing, reduction of errors, and which one has a better accuracy is what will be seen and will be given as an output, right? This is what happens with your bagging model, right? As an example, as I told you, random forest is a popular bagging model which we are work with, where multiple decision trees are combined to get a better performance. And with this bagging model, you can actually we can actually use it for classification, which means voting, and also for your regression, which is nothing but averaged prediction, right? Nandita, you have an idea about differentiating between voted and average, right? These terms, which are alternative terms for your classification and regression. Let me know, or else I'll just give you an explanation about it. నందిత గారు మీకు నా వాయిస్ వినిపిస్తుందండి?
యాహ్! వినిపిస్తుందండి.
సో మీకు ఇది ఓటింగ్ అండ్ యావరేజ్ అనే దానికి డిఫరెన్సియేషన్ అయితే తెలుసు కదా! ఇట్స్ నథింగ్ బట్ అదర్ టర్మ్ ఫర్ యువర్ క్లాసిఫికేషన్ అండ్ రిగ్రెషన్.
ఓకే. అంటే ఇప్పటి వరకు క్లాసిఫికేషన్, రిగ్రెషన్ అనే
కరెక్ట్.
అనుకున్నాము. సో,
సో
యావరేజ్ ఇది ఫస్ట్ టైమ్ వింటున్నాను. బట్
ఫైన్.
ఇట్స్ ఓకే.
నేను ఐ విల్ ఎక్స్‌ప్లెయిన్ ఇట్ టు యూ.
ఓకే.
So whenever we say regression, it's nothing but you are actually trying to get an average of what has been given to you based on the trained data. That's where you are averaged a word which comes ahead, a term which comes ahead. అది మీరు పెద్దగా ఐడియా ఉంచుకోవాల్సిన అవసరం లేదు. బట్ ది అదర్ టర్మ్ విచ్ ఐ కాల్ ఇట్ యాజ్ వోట్. Now, what do you mean by vote? Ante vote is another term which we use for classification. Now, basically, what happens with a classification model is that each and every classifier, each and every class of your data, the machine learning model is going to vote for it, that which one has a higher probability of that class. That's where this term, which is called as vote, comes ahead. Ante, simple, there is nothing here. Just like how the politicians are going to be voted, that's the way machine learning model is going to be voted based on the, that's where the machine learning model is going to vote the class based on the probability which they get, right? The terms have to be, you have to remember these terms. The reason why is because sometimes in an interview, in order to trick you, right, the interviewer is going to talk about these things. Just give me 1 minute. Yeah, just to trick you, the interviewer is going to talk about these terms. So that's the reason. Just have a idea about this voting and also averaged, right? Now the key points of ensemble technique, sorry, bagging models are, they are independently trained. That means each model is, just give me 1 second. I really don't know why these notifications are coming right away. Yeah, my bad. I'm very sorry about it. Now, the key points which you have to remember with this bagging model is models are trained independently. Now, when I say sorry, random forest, just like your normal forest where you have multiple trees, your random forest is going to be built on multiple subsets independently, meaning one model might have a really good high accuracy with the subset of data which they have, but the other model which is going to build under this decision random forest is not going to be affected. The second key point which you have to remember is parallelism. Let me write it down here. Bagging. Bagging. That is, first point, independent. Parallelism. Parallelism. Now, when I say parallelism, bagging can train multiple models simultaneously, right? That's what is happening here. 80% of the data has been taken and it's been split into 10 subsets, and these 10 subsets are run simultaneously at a time, right? And this bagging model focus on variance reduction, which means prevention of overfitting has been a key point for here, right? Variance reduction is also a key point for your bagging model. Now, what models do come under this? Your random forest and decision tree are the best examples for your bagging models. I hope we are clear with the bagging. Now we enter to a different dimension, which is called as boosting models. Now, what are these boosting models? Now, few key points. One of the key point which I would like to pick from the bagging is parallelism, which is nothing but simultaneously the model is run, right? Which is more efficient. But when it comes to your boosting, right? When it comes to your boosting, they are called as sequential learners, right? Let me put it down here. They are called as sequential. Sequential learners, right? Now, when I say sequential learners, what's happening here? Now, the same data set has been taken, which will be as a subset. It will be, I mean, it will be split into subsets using a sequential, sorry, bootstrap sampling technique. But The small difference here, which you see with boosting, is the models are built sequentially. Now, if we are going to take the 10 subsets which we have previously, and here also in the boosting technique, we are going to work with something which is called as decision tree itself. Decision tree won't go anywhere. It will be a base model, but utilizing this decision tree is being changed right now. Now, these 10 subsets will be built one after the other. The first subset, post second subset, third, fourth, fifth, sixth, so on till 10th subset. Now, due to which what's going to happen? The time taken to build or get your result of the model is going to be increased. But, right, there is a good reason why this happens. But the sequential model depends upon what has been built previously. Now, when we are going to talk about the sequential model, there is a thing which I would like to utilize, discuss here, which is called as cache, which you might have obviously heard about. Now, this cache terms comes when you are actually working with something which is called as browsers. Now, with your Chrome browser or any browser, if you are going to open a web page multiple times, what your browser is going to identify is that you have opened a page multiple times. To reduce the time of load, what your browser does is it's going to save the entire page in the backend, so that whenever you want to open it, it will be displaying it to you very quickly, due to which your storage size is going to be increased. Now, the same thing happens here also. Now, I said here only a 10 subset, but reality, when we go into the live use cases, which we are going to work with, there the data set is going to be subsetted into sometimes 5,000, 6,000, 7,000. We don't know. Until we get a really good accuracy, the subset of the data is going to be happened. Now, why I say that sequential learning is a really good technique is because, as I told you a minute back, that dependency of model build is present here. That means previously when we were discussing about bagging, where independency is there, that means one subset of the data has been trained, there you see a really good accuracy and less errors. That doesn't affect the next model. The result doesn't affect the next model. But here, what generally does a sequential learner does is, it depends on the previous one, where the errors are carried over here to improve the accuracy and reduce the errors. Right now, let's say, for example, your first subset model which has been built, where you have a good chunk of errors, and with the second subset of data, it's going to identify the patterns there, and obviously it's going to also consider the errors which are done previously by the model. It's going to consider that errors too and improve the accuracy here. Right, it improves the accuracy based on the previous errors. Right, so that's where the sequential learners come into a picture. Now, the reason why I was actually talking about cache is because now the number of subsets which your boosting model is going to split sometimes depends upon your hardware capability of your system, memory utilization, computation. These all things will depend upon your cache itself. Your hardware dependency itself. So these all things will be considered by your boosting models. Right? Just like your bagging, your boosting can also be used for voting and also averages, weighted averages. Right? Now, the key points which you have to understand from this boosting model is that dependency between the models will be present with your boosting, and bias reduction will be done. Now, previously, our main focus was variance reduction, but here with boosting is we are actually working with bias reduction, which means we are not trying to make a simple machine learning model. We are trying to make something which is called as a complex machine learning model, which is going to increase the variance, which means the overfitting is going to be increased here, right? Overfitting is going to be increased here. Now, obviously, we have a certain set of things which we can do to reduce the overfitting or to, you know, control the overfitting going through regularization and, experimenting through your parameters using k-fold cross validation, and all these things are present, right? This is where your boosting techniques do lie. So I hope you are able to understand about this boosting technique where we are actually utilizing our hardware capabilities, right? I would like to stress on this point where we are actually trying to utilize something which is called as hardware capabilities. I am afraid to say this point, but some scenarios we have actually seen that a better hardware devices with this boosting techniques where the accuracy and the learning techniques were really good, right? Compared to your uh, boost bagging models, right? Normal hardware models also. Now, I would like to introduce to a topic which is called as computation and also CUDA here. Now, this is a topic which you will be learning when you are actually working and also during the introduction of deep learning models. But this is a good time for you to introduce about something which is called as CUDA. Now, the reason why I'm talking about this CUDA is because this has been a revolution in your AI space, right? This application has been a very big revolution in your AI space. Now, the reason why I say this is because let's say you brought a laptop. Now, if you go through specification, they're going to say like you have 12 core processor, and you have around 16 GB of RAM, and you have a 1 TB of storage and blah, 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 and all the things. And you have 6 GB of graphic card, and all the things will be specified under your specifications. Now, when you try to build a boosting model, or when you try to work with any machine learning model, not specifically a boosting, do you think all 12 cores will be assigned to your machine learning model and you're going to work with that? No, that's not going to be the point here. Only one or two cores will be assigned to your Python application, and where you can actually utilize, right, your your Python to build a machine learning. So out of 12 cores, you'll be utilizing only two or three cores to which will be allocated to your Python to work with machine learning, right? Now, what is a cache here? Even coming to your 16 GB of RAM, the entire 16 GB of RAM will not be allocated for your Python. Now, I hope you know about RAM. RAM is nothing but random access memory, which is nothing but a temporary storage of your files. Now, entire files will be stored in your hard disk, but in order to view it, the file first has to be fetched from your hard disk and it will be temporarily stored in your random access memory, which is nothing but your RAM, and then it will display it to you. And then once you close that particular application or your file or your image, it will be removed from your RAM, right? That's where your RAM comes into the picture. Even the same thing happens with your RAM also. The entire storage or the temporary storage which is available with your RAM will not be allocated for your Python, right? That's where your CUDA comes into your picture. CUDA stands for Computer or Compute Unified Device Architecture. I know this is a way advanced topic which I'm actually discussing with you. Now, the reason why I'm actually discussing is because in boosting itself, we have got a new model which is going to work under this CUDA principle. So that is the reason. Now, what does this CUDA does? Every one of us know about something which is called as graphic card, which is present in your system or your laptop. Now, what is the reason or what is your main function of your graphic card do? And I'll just extend the class by a few minutes, just understand it, because I just want to complete this topic. And tomorrow we are going to work with the models which are present under your boosting, right? Now, what does your graphic card do? What is the main procedure or main work of your graphic card? Your graphic card main work is to render an image and show it to you on a higher resolution. That's it, right? Beyond that, your graphic card has not been used. Now, rendering the images in the sense like when we are actually playing games, watching high resolution videos, this graphic card comes into a picture to show you in a very good manner. Now, what happened with this particular organization, which is called as NVIDIA, which was and also is a mass producer of graphic cards. These people are mass production. I mean, these people have a high range of a graphic card manufacturer in the market. In year somewhere around 2015 or 2016, when they were actually working with some artificial intelligence model, and they were not able to utilize the 100% capability of the CPU, the internal engineers come up with an idea saying that why don't we use our graphic card, right, which we are going to install in every system or designated system for computation, right? Now, instead of allocating 12 out of 12 cores, allocating 2 or 3 cores for your Python, using an architecture which is called as CUDA, why don't we work with, or why don't we use the graphic card for computation process or computation procedure? That's where a head turning point came up with. My bad, just give me 1 second. That's where, this NVIDIA has changed their policy. They are no longer building a graphic card for visualizing the data or rendering the data. They are more towards computation right now, right? So what they are actually doing right now is using this application or an architecture which is called as CUDA. They are allocating the entire 15 or 16 cores which are present in your graphic card for computation, and also, as I told you, like 6 GB or 7 GB of graphic data, right now, graphic card storage, the entire 6 GB or 8 GB, whatever the size of the graphic card, for your random memory, right? Along with your RAM, they are going to allocate some memory from entire memory which is available in your graphic card for storage. That's what this architecture does. CUDA. Remember this point, because we are going to work with this CUDA when we are actually uh, working or learning about deep learning models, right? Now, why are we actually introducing this boosting model with, or why are we linking up this boosting model with CUDA is because we had a new model recently developed, which is called as Cat Boost. I know the name sounds a bit silly. Believe me, this is a machine learning model, which is called as cat boost. Now, what does this cat boost does? It allows you to utilize your GPU for computation. Previously, whenever we are going to build a machine, sorry, boosting model, we were actually working with few things which are called as uh, core utilization of your CPU and random access memory. That's what we are actually using. But with a model which is called as cat boost, I'll just give you the link for that also. They are actually linking that as an AI model, but still it's not an AI model, it's an ML model itself. But this cat boost allows you to use graphic card for computation, right? That's where your boosting model stands right now, right? And this is where I would like to end the class for today. Please let me know if there are any doubts. And what we are going to do in tomorrow's class is basically we're going to work with the different boosting models which are available, right? On a same note, we are going to compare between your bagging and boosting models. I don't say they are like neck and neck comparison between two things, and I can't just give you a guarantee on, bagging model is best with the certain set of data or boosting model is best with a certain set of data. The thing which I would like to point out when I say we are actually going to compare it, my main agenda is to show you that we are taking consideration of the time taken to build a model and how the variance and bias are going to look like. Now, just to differentiate, bagging will work on bagging where the model build is done parallelly and boosting where the model build is done sequentially. Bagging, we are going to focus on reduction of variance, and boosting, we are going to work on reduction of bias, right? And with bagging, we have low risk of overfitting, and with boosting, we have high risk of overfitting, right? So these are few key differences between your bagging and boosting models. So I hope you are clear. I'll stop the recording here.